All right, let's dive into one of the most important, but also one of the most misunderstood concepts in all of physics. I'm talking about an idea that governs literally everything, from why time only seems to move forward to the very reason that you and I are here to begin with. It's called entropy. And to see why it can be so tricky, we really only need to ask one simple sounding question. What does the Earth actually get from the sun? Now, most people would say, well, energy, right? Heat, light. And yeah, they're not wrong. Every single day, a huge amount of energy from the sun hits our planet. But here's the follow-up question. How much of that energy do we radiate back out into space? You'd think we must keep more than we give off, right? I mean, we use that energy for everything. Growing crops, driving our weather, powering life itself. But here's the thing, and it's kind of surprising. For the Earth's temperature to stay more or less stable over the long haul, the amount of energy coming in has to be the same as the amount of energy going out. It has to balance. If it didn't, we'd either boil or freeze. And that right there is a fantastic paradox. If we're just breaking even on energy, if the total amount doesn't change, then what are we really getting from the sun? What is that special something that makes all the difference? To figure that out, we have to travel back about 200 years to a discovery that completely changed our understanding of everything. So this is our solar energy paradox. And our first real clue for solving it doesn't come from looking up at the stars, but from the heat and the steam of the Industrial Revolution. Yeah, it turns out the quest for a perfect, 100% efficient engine led scientists to discover a fundamental limit, a cosmic rule about energy that no machine, no matter how perfect, could ever break. So picture this. It's the early 1800s, and this French military engineer, Sadi Carnot, is completely obsessed with steam engines. The best ones at the time were, well, they were terrible, only about 3% efficient. So Carnot starts wondering what's the absolute best an engine could possibly be. What's the theoretical maximum? So he designed a perfect, ideal, totally frictionless engine, all in his mind. His ideal engine works in this neat 4-stage cycle. First, you have a gas. It expands while it's touching a hot source, and that pushes a piston up. Simple enough. Second, you take the heat source away, and the gas just keeps expanding, but now it starts to cool down. Third, the piston pushes back down, compressing the gas while it touches a cold reservoir. And finally, you take the cold part away and compress the gas just a little more, which heats it right back up to where it started, all ready to go again. And this is the crucial insight Carnot had. It was a game changer. Even in this perfect, imaginary, frictionless engine, you can never get 100% efficiency. Why? Because to get that piston all the way back to the start, to make the engine run continuously, you have to dump some of that heat into the cold reservoir. You just have to. You can't turn all of the heat into useful work. Some of the energy must be discarded. It's unavoidable. So this idea that some energy inevitably just kind of gets away, becomes unusable, that leads us directly to the concept that puts a name to it all. It's all about energy's natural, unstoppable tendency to spread out. And this is that concept. Entropy. Now, you've probably heard it described as disorder. For right now, I want you to just take that idea and toss it out the window. The best, most useful way to think about entropy is as a measure of how spread out or dispersed energy is. That's it. So energy that's concentrated, like in a hot piece of metal or the fuel in your car, that's low entropy. It's useful. But energy that's spread out, like the waste heat from an engine, that's high energy, and it's way less useful. A few decades after Carnot, a German physicist named Rudolf Clausius put it all together perfectly. He famously laid out the first 2 laws of thermodynamics. First, the total energy of the universe is constant. And second, the entropy of the universe always tends to a maximum. In other words, over time, on its own, energy just spreads out. But why? Why does energy always spread out? Why do hot things always get cold in a cool room and never the other way around? Answering that question reveals something incredibly profound about the nature of time itself. The answer came from another physicist, Ludwig Boltzmann, and his insight was revolutionary. It's not that there's some cosmic rule that says things must get messy. It's just a matter of pure, overwhelming probability. Think about a Rubik's Cube. There is exactly one way for it to be solved, but there are quintillions, literally quintillions of ways for it to be a jumbled mess. So if you just start turning it randomly, what state are you most likely to end up in? It's the exact same logic for energy, but on a scale that is just impossible for our brains to comprehend. There are vastly, vastly more ways for energy to be spread out evenly across all the atoms in a system than for it to be all concentrated up in one little spot. The universe isn't trying to be messy. It's just that the messy, spread out configurations are astronomically more probable. So let's go back to that lukewarm cup of coffee. Could all the molecules in it suddenly, randomly coordinate their vibrations to make one side piping hot and the other side ice cold? Well, technically, it's not impossible. But it is so staggeringly, ridiculously improbable that you would have to wait trillions upon trillions of lifetimes of the entire universe to ever see it happen. It just doesn't happen. And this constant, unstoppable march from the less probable states to the more probable states, that is what gives us the arrow of time. It's why we remember the past, but not the future. Okay, so now that we're armed with this powerful idea of entropy, let's rewind and go back to our original paradox. What is the sun's real gift to the Earth?
And here's the answer. It's not the amount of energy that matters. It's the quality of that energy. The sun is giving us a constant stream of really high-quality, low-entropy energy. It's all concentrated in a relatively small number of high-energy photons. The Earth then takes that energy, uses it, and radiates the exact same amount back out into space. But it radiates it as low-quality, high-entropy energy, all spread out over many, many more low-energy photons.
And to put a number on it, get this. For every single high-energy, low-entropy photon we get from the sun, the Earth sends about 20 lower-energy, high-entropy photons back out into the coldness of space. The total energy stays the same, but the entropy has gone way, way up. So what's happening in between? What happens in that process of turning one really useful photon into 20 less useful ones? Well, everything. Literally everything. Life itself exists in that flow. Plants are these amazing machines for capturing that concentrated sunlight. Then animals come along and eat the plants, spreading that energy out even more. Every single thing that happens on our planet, a hurricane forming, a herd of wildebeest running, you and me living and breathing, it's all part of this grand cosmic process of taking the sun's low-entropy gift and increasing the total entropy of the universe. So if the sun is our local source of low entropy, it makes you wonder, where did the sun get its low entropy from? And to answer that, we have to zoom out, all the way back to the very beginning of the universe itself. See, if we follow the arrow of time backward, knowing that entropy is always increasing as we go forward, then we have to conclude that the universe must have started in its lowest possible entropy state at the Big Bang. Now, this sounds weird, I know. The early universe was a hot, uniform soup of particles, which sounds messy. But, and this is the trick, when you factor in gravity, which loves to pull things together, a perfectly smooth, uniform distribution of matter is actually an incredibly unlikely, very low entropy state. From there, gravity got to work, pulling matter into clumps, forming stars and galaxies, and in doing so, increasing entropy and making our present possible. And the far future? That's the heat death, a state of maximum entropy, where energy is so perfectly spread out that the arrow of time just stops, and nothing interesting can ever happen again. This idea is so fundamental to our existence that it actually has a name, the past hypothesis. It doesn't explain why the Big Bang was so incredibly orderly, just that for a universe like ours to even exist, it absolutely had to be that way. That initial, pristine, low-entropy condition is the ultimate source of every useful bit of energy that has ever existed anywhere. And the numbers, I mean, they're just staggering. It turns out that almost all of the entropy in the universe today is locked up inside supermassive black holes. The entire early universe, everything, had only a tiny fraction, about 0.0000000000003% of the entropy it has today. This huge potential, this enormous, vast room for entropy to grow, is the very reason anything at all can happen. It's the engine that's been driving the entire cosmos for 13.8 billion years. So this leaves us with a final, kind of beautiful thought. Entropy isn't just this destructive force of decay leading to a boring, uniform end. Think about what happens when you pour milk into a cup of tea. The most beautiful, complex, swirling patterns don't happen at the beginning when they're separate, or at the end when they're fully mixed. They happen in the middle, during the process of mixing. So, is that what we are? Is all the stunning complexity we see around us, from spiral galaxies to life itself, just a beautiful, intricate, and temporary pattern that emerges as the universe's energy simply follows its inevitable path, spreading out from its incredibly unlikely beginning?